If you don't follow these calculations, you have to go back to the order chapter of the book and make sure you do this type of computations. Okay, now that we have, I'm a bit out of space here. What I will do is I will squeeze this, I'll just erase this of degree 2. Because you've already seen that, so now okay, and then I keep on working here, so we get to the end of this. So now, my function f of xy is equal to 2x plus y. This I get from here. And then I take from down there, plus 1 minus x plus 2y, divided by 2. And a square there, plus ordo yeah, so that's the same order term. It's just to the power of 3 here. That's norm xy to the power of 3. And now, okay, so when you solve the exam, I guess you know this by now, I hope, because you've done several other exams, you have to write down in a structured way each step. Not like me here, because I'm continuously talking while I write it down. If I just get something that looks like this without any comments, no logical thread, I'm not going to give them any points for it, even if maybe you can guess that the person thought correctly. Come on. So this is education in mathematics, but also, I mean, an integral part of that is being able to present mathematics in written and also in spoken. Unfortunately, due to Corona, we don't practice the spoken part enough, but at least the written one, I mean, you should be able to write a solution in a way that another person can read it and say, okay, yeah, I understood what he was doing here. So a bunch of scribbled down computations, which are correct, but with no logical chain of thought, is not giving you a full score. I've forgotten the 2 times. Yes, thank you so much. The cosine term is 2 times. Right, so there's a 2 here, and there's a 2 times this also. And here there is not the 2 times, because the ordo notation eats up any constant. So we don't need, of course, we could write 2 times the ordo, but that would be just looks stupid. It's not wrong, it just looks like you don't really master ordo. Okay, so what do we have here? We can write this as a polynomial p of xy plus ordo x comma y to the power 3, where p of xy is equal to 2, sorry, yeah, 2 plus 2x plus y minus x plus 2y squared. Yeah, because this 2 and that 2 cancel out. Right, so does this tell us that this is the Taylor polynomial of degree 2? Yes, it does, but that is a theorem. So another thing to get full score is that you mention this theorem, so you don't like just, you know, some people with a vague understanding of mathematics don't have a good idea of what's trivial and what's something that needs a proof. This is something that definitely needs a proof, and that's why we have a theorem which proves that in the lecture notes for the Taylor polynomials. I'm a bit uncertain if the theorem is in the book. I think they mentioned it, but maybe the proof is not there. But anyway, the proof is in the lecture notes. Anyway, there is a theorem. If you have a polynomial of degree k, an ordered term of degree k plus 1, and that equals your function, adding the 2 up, then the polynomial is unique. That is your Taylor polynomial. So you have to mention the existence of this theorem. I often get the question, okay, so how can I call the theorem? Most theorems don't have names, right? So just write by the theorem which says that okay, so what would I write in a case like this? It's not really important how you write it. By a theorem on uniqueness of Taylor expansions, we know that blah, blah, blah. And then often these theorems have conditions you need to check. Like in this case, the degree should be less than 2. The ordered term should be then 3. So then you write, look, the polynomial has degree 2. The ordered term has degree 3. By the uniqueness theorem, I know that this is my Taylor polynomial. So like that, you mentioned some stuff in the what goes into the theorem. There's no doubt that you know the theorem you're talking about. As opposed to just writing it a little bit here and there, by a theorem in the book, by a theorem in the book, by a theorem in the book, in random places, I'm going to figure out that you don't actually know which theorem you're talking about and just guess. So as long as you just the reference to a theorem comes in the right place, and you just write something like by the uniqueness theorem or whatever, that will give you. We are flexible or generous here, so we try to interpret things to your favor. So don't worry too much about exactly how to call theorems. Okay, so this is our Taylor polynomial. Let's go back to the exam and see. So we needed to also compute the value at the point, right? So I'll do that first, and then I'll do strategy 1 for getting the same Taylor polynomial. Use this to approximate this value, f of 0,1, f of 0,2. Sorry, f of 0,1, 0,2. So f of 0,1, 0,2 is approximately equal to, and what you do is you just throw away the ordered term. Because here we have no idea, ordered term at the distance, now where are we? We're something like 0.25 away from the point. That's not a really small distance, so we can't be sure that ordered term is all that small, but you know, if you're uncertain about this, you can always do this Lagrange reminder, and then you get really an upper bound to the error term. We don't do that now. So we're just going to approximate it by the polynomial value, and that's easily computed. So 2 is the value of my function at that point, and then I get plus 0.4 from here, and then I have a minus. Okay, so this is a 0.5, right? Squared. So 0.025. 0.5. No, sorry. Right. So half of 0.5 is 0.25. All right, and that's 2.15. So that's your approximation. All right. Back to strategy 1. How could we get this polynomial there? Using the definition. so again, the function was 2x plus y plus 2 cosine x plus 2y. So then we just have to compute all the derivatives. So this is a very boring way. So fx is equal to 2 minus 2 sinus x plus 2y, which at 0 is equal to 2. All right, and that's the same 2 as we were getting here. Fy is equal to 2 minus, it's the same, but now there comes an inner derivative from here as well. So we get minus 4 sinus x plus 2y. So Fy at 0 is again equal to, sorry, no, it's not, sorry, here is a 1. I'm differentiating y, so then it's a 1, which corresponds to what we had before. Now, a bit interesting is the second order term, because here's a factor 1/2 that I always forget. So let's do this guy. So now I can, so then I differentiate him. So that's, this one goes away, and this is a minus 2 cosine x plus 2y. And then fxx at 0 is equal to minus 2. Right, now let's I'll just skip the computations here. So this should be minus 4, and this here should be a minus 8. Okay. So what are then ways of writing down the Taylor expansion? So this polynomial P, the Taylor polynomial to the second degree, it's equal to the constant value. Actually, I didn't even write that here. So f of 0 is equal to 2. So we get 2. Then we get first derivative. So that's a 2 times, okay, let me have here new variables, p of h and k, right? So we usually, when we do perturbation analysis, instead of calling them x and y, we call them h and k. In the previous one, I called them x and y still, especially when the point is 0. This is often convenient. It doesn't really matter. But now, okay, so there is an h coming from there. Then I have plus 1, which is this derivative, times k. And now I have plus a term where it's very important to not forget to write the square. So sorry, the half. This one sits always in front. And then we have so now minus 2 h squared minus 2 times 4 hk and minus 8k squared. Yeah? And this all together, we see that this can be written as minus h plus 2k squared, right? So the mixed term here gets a 2 in front of it. That's one thing you can't remember, forget. The other thing that's easy to forget is this 1/2 in front. other ways of writing this is to use this Hessian, right? So the Hessian is -2, -4, -4, -8. And then we have HK here and then scalar product with HK. But even if you use this Hessian notation, don't forget to put the 1/2 in front. All right. Now, yeah. This is the guy, if this had been a local minimum or max, this is the guy you analyze if you want to know if it's a local min or max, if that was a stationary point. But this question is not about that, so let me not even go into it. That concludes that solution. Are there any questions? No questions. I said we will have a break, so I'm going to do one more exercise and then we will have a break. I think I don't think I know I made this exam. That's why the questions are a bit on the silly side. A person walks around on a road on a hill with the shape yada yada. The projection of the road in the XY plane is the unit circle. Which are the points of steepest ascent, descent, and how steep is it there? So what's our question function here? F, X, Y. -30 minus X plus 2. All right, so, and then, okay, so this is, right, I'll just do the A part first and then we'll do the B part. So, all is not really called for, it's always good to paint the picture. Here's X, here's Y, and this surface, we can actually understand it pretty well. So this is a hill, which is 30 meters high. And then you have this parabolic shape going down. And the center of the parabolic is at X -2 and Y equals to 0. So this is a hill with the center -2 and Y value 0. And then it sits 30 meters up. So it's a pretty high hill. Let me write 30 there so the scaling of the Z-axis is a bit different. And then, okay, so one side, so I mean, this hill is very big. It goes down something like this, right? So the slow decline is due to I scale the y-axis a bit differently. Okay. And then we have the guy who walks around like this. In the XY plane, it's just the unit circle, which means that up on the hill, is going up and down on the slope of this hill, right? So, I mean, just by painting, you can figure out that this is the lowest point and this is the highest point. But it doesn't really tell you which point has the highest slope, but it should be somewhere around here is going down and on the other side is going up. So somewhere, okay. But how do we do this? Well, there are a few ways to approach it. But basically, this is a one variable problem. So I think the most direct way of doing this is just parameterize your curve in the XY plane. And then you get a function of your parameterization. So you do gamma of t cosine t sinus t. So this is, if it walks with angular velocity 1, this is t could be time. So it just goes around like this, equally fast on the upslope as on the downslope. And now we do f of gamma. Gamma is a vector. Let me put a bar on it. Of t. This is equal to 30 minus cosine plus 2t squared minus sinus squared t, which in turn is equal to what the hell happened here? Cosine t plus 2, I don't know, not really thinking today. Okay, so this gives me 30 minus cosine squared t minus 4 cosine t minus 4 and minus the sinus squared t. And this is the trigonometric identity. So in the end of the day, we have 25 minus 4 times cosine t. Actually, I got confused now myself. So, all right. So what we have here is a function that describes the height of the guy as a function of time, and he moves with a constant speed. So if we differentiate that, we get how many meters up or down he goes per second. And since the speed he moves with in the XY plane is constant, that should correlate directly with how steep it is. But of course, if his speed is not equal to unit 1, it's not so clear, maybe. Oh, question here. Yeah, we could compute the gradient. Once we find the point, I mean, okay. So yeah, I think this one is maybe leading us on a bit of a sidetrack. So the value of the slope, okay, so at each point on this curve, it has it moves in a certain direction, right? So let me call this direction u, and it also depends on t. So okay, u of t is then equal to, And that we get by differentiating our curve. So that's a minus sinus t, cosine of t. And then the gradient of f at some point x and y is equal to minus 2x plus 2, comma, minus 2y. So the steepness of the slope at the point here is, by definition, it is directional derivative at that point. Okay? So what is the directional derivative in the direction of u of f? Now, of f where? So this is u of t at the point gamma of t, right? So you take a directional derivative here of the function f in the direction of the motion. Yeah? So that would be scalar product minus 2. And here I insert then the value on my curve. So cosine t plus 2, comma, minus 2 sinus of t. So that's the first one. And then I have this vector u, which is minus sinus t, comma, cosine t. So this is the directional derivative at that point. It gives how steep it is going down or going up. So by finding the maximum value of this, or minimum value, we get the steepest points in the direction of motion, because this is what we're interested in, right? In the direction he's moving. So what is this then? This is a 2 sinus t cosine t minus, okay, so plus 4 sinus t and that is a minus 2 sinus t cosine t. All right. That one cancels that one out. And at the end of the day, we have 4 times sinus of t, which kind of corresponds with our picture here. So what this is telling us is that actually the steepest increase is exactly when we hit, when t is pi over 2, so when we have 90 degrees here, then it's going maximum up, and the slope there is 4, and correspondingly here, it goes maximum down, and the slope is then minus 4, because sinus of t is plus 1 over here, minus 1 over there, right? And that makes sense. So then the zero slope is at this point and that point, and that, of course, is corresponding to our intuition here. So, yeah. Steepest upward slope is 4 at the point 0, 1, and then what's the value? If I put 0 and 1, I get 25. as the C value. Okay. Do you accept this solution? So now if we go back to what I had going there in the first place, there's a 25 minus 4 cosine t. If I differentiate that, I get minus 4 sinus of t. So it probably would have led to the same thing, but I'm not sure exactly how to motivate it, because now we kind of consider like a moving object. It's a bit more complicated. The second solution is more clean. Did we miss the minus 4? I don't see a missed minus 4.
I think he means the point on the other side of the hill. So he goes up and then he goes down again. So now we have just 1 point.
Yeah. So the steepest upward slope is 4, and then the steepest downward slope is minus 4. That's on the opposite side. I just didn't feel like writing it down. Yeah, so correct. So there are 2 points. Two. Here is 2. So what is the B? Right, and this one, I don't know the B solution. I guess this one was added for people. If you don't do this with a directional derivative here, but solve it in some other way by, like, along with what I did in the first one, this B part here is just basically controlling that you know how to compute directional derivatives. Maybe, well, okay, let's do it. So straight northeast, what means that? So if this is planet Earth, so first of all, here at this point 1, 0, up on the surface, the height here is 21, yeah? Because 30 minus 3 squared, that's 30 minus 9, it gives us 21. And now the question is, what is the slope in the direction northeast? Well, y-axis would be pointing north, x-axis would be pointing east, right? This direction is China, this direction is North Pole. So then northeast is this direction, right? So northeast, but then we want to compute directional derivative. So we want now the directional derivative direction northeast, yeah? So how we do that is, all right, so the directional derivative, you take a scalar product with the direction, but you always normalize first. So the direction north east is given by vector 1, 1. Let's call this u. The directional derivative in the direction u of f at the point 1, 0. Again, it's the derivative, which is this one. So at the point 1, 0, I have minus 6 and 0. And then I do a scalar product with 1, 1, but I normalize. So square root of 2, right? So at the end of the day, the directional derivative is minus 6 divided by square root 2, which is the same as 3 times square root 2 with a minus. So that's directional derivative in that direction. Okay, so I promised there will be breaks. It's a bit short now for a break, but let me run up and get a cup of tea, and then in 15 minutes we'll solve another exercise. So short break, and then we do number 3 and probably 4, 5, 6. I will do them on lunch hour today. All right. I'll be back in no time. All right. So back again. A cup of tea. All right, now another stupid exercise. An infinite size egg carton is given by whatever. Determine all critical points and classify them local, global, min, max, saddle point, etc. This one, okay, so if you did the exercise I told you in the beginning to write down like a blueprint of how you would approach this, I think most of you would write, well, I compute the first and second derivatives and do my, find zeros and do my Hessian and all of that. Like just follow the standard procedure for these things. You compute gradient, set gradient to 0. At those points, you investigate how the second order terms look like to see if it's local max min or what it is. The problem here is that we have infinitely many max and minima and saddle points because these functions right there are periodic. And it just becomes very hard to keep track of which point is what. So it's much easier here if you first do a change of variable where you kind of split up or take, put the cosine term with one of the variables and the sinus term with one of the other variables. So I think, yeah, this should probably have been a hint actually for this exercise. But anyways, so change of variable is something we've worked with, so something you should know. So it's good to revisit that. So if we have, so set u equals to x plus y and v equal to x minus y, I think it is. If you read Callahan's book, you also know a lot about how to visualize this. So in the end, if this is the UV plane, here's the X and Y plane, then basically this says that so the vector 1, 1 is like your basis vector for X, and then the vector 1 minus 1 is your basis vector for the y variable. So a coordinate xy would in the UV plane, a coordinate which is here like 1 and 2 would here correspond to, you go 1 in this direction and then you go 2 along this direction, so you end up somewhere here. So we see that this change of variable kind of blows up things a bit and become bigger here because the length of these two vectors is square root of 2. and also flips the direction. So here the y-axis is to the left, but here somehow the y-axis, we can think of this as the y-axis, right? So it sits to the right of what we can think of as the x-axis. Okay, so understanding, visualizing changes of variable is good. Sorry, I should stop share, but not necessary. So here we have that f of x, y is equal to g of u, v through this change of variables, right? So we just define a function g such that this is true. Then clearly f at the point x and y as a minimum, maximum, saddle point, whatever, stationary point, if and only if g has the same at the corresponding point in the UV plane, right? If we want, we can of course solve here. So this means we can solve this equation system. Then we get that x is equal to u plus v divided by 2, and y is equal to u minus v divided by 2. So g of u v technically means f evaluated at these coordinates. That's what it means. Anyways, so if we find the local maximum minimum of g, we find the corresponding ones for f, and finding them for g is much simpler. So technically, I mean, I should write down f and g have stationary points. You know, if one has a stationary point at x, y, the other one has a stationary point at u, v, yada, yada. But I've said it now, so I'm not going to write it down. So we look for stationary points of G. And okay, so what is G? G of U and V, I mean, you don't need to compute actually this backwards change of variables, because here I chose it so that when I stick it into my function, which I haven't written up, okay, but my function is cosine x plus y and sinus x minus y, right? Let's look at the function again. Five cosine x plus y plus 3 sinus 2x minus y. Okay, so it was a bit more complicated than that. So it's 5 cosine u plus 3 sinus 2v. Okay, so the nice thing here is that now in the UV plane, we're gonna get a grid of points. It's very easy to keep track of who's a maximum, who's a minimum, and actually can almost see where they're gonna be by simply painting here, right? Because cosine u, so in order for a point to be stationary, it needs to have a flat x u derivative and a flat v derivative. So we need this guy to have a flat derivative, meaning that we're at the point like 0, pi, 2 pi, and so on. So we know here that this point is going to be important, and then pi, and then 2 pi, and minus pi. And similarly here, what are the points? So this one has maximum at pi half, minimum at minus pi half, and then this iterates with interval pi. But because of there's a 2 sitting here, the points of interest here will be pi divided by 4, and then plus pi half, and so on. We have minus pi divided by 4. So I could have written 3 pi divided by 4, and so, right? So the points of interest, even without any computation, just knowing your sine and your cosine, you see that they are when the u coordinate is in either of these points and the y coordinates is in either of these points. So actually, the grid we're gonna get is this point, not that point. That was just me painting on the x-axis. This point, and then the corresponding guys here. This one, 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 so on. So we get this really nice grid behavior. So, and we can also easily see which are going to be our maximums and minimums, because this is a function that ranges. I mean, cosine goes between +1 and -1. Sinus 2v goes between +1 and -1. So the maximum here is clearly 5 + 3, 8. And where is the max happening? So here at 0, cosine has a maximum, and when sinus hits pi over 4, the sinus also has a maximum. So here I get an 5 + 3, so that's an 8. So this is max. But then up here, sinus has a minimum, but cosine has a max. So in the u direction at this point, you will have an upwards derivative, second order, and in the y direction, in the v direction, you will have. In the u1 you have a maximum, so it goes down, and in the v direction it's a minimum, so it goes up. So we clearly see that we have a saddle point because it behaves like a positive quadratic in one direction and a negative quadratic in the other. So here we have saddle, max, again saddle. And then we have a max again, right? So there are no minimums here because the cosine term on this line is always +5. Over here, cosine term is always -5, right? And the sinus term is -3 when we hit this point. So here we get like an opposite behavior. We have a minimum, we have the saddle, and then you have a minimum. Okay? So we get some sort of chess pattern here of maximums and minimums that we can get by just knowing our sinus and cosine functions and think of it. So, max happens at, so the u coordinate needs to be a plus, which means that the u coordinate should be 2 pi times k, right? So cosine hits +1 every 2 pi with center 0. And the y coordinate should be pi over 4 plus, and now this repeats, so that's that point here, pi over 4. And then sinus hits a max, of course, also with period 2 pi, but since there's already a 2 there, the period is pi. So let's write here pi equal, so L is the letter that comes after K. So for K and L being natural integers. So this is the more mathematical way of writing it. So now we get this point, and then over here is another point, the same. Min happens at, so now we have pi plus 2 pi k, and here we could write minus pi over 4 plus pi L. And the rest on the grid here is saddle points. Okay, so if we want to, but if we just look at the max points, so now we found all the max points, they happen here. This is in the UV plane, right? So if we want to go back to the XY plane, we have to send it through this one. So max is found at points, I'm just writing here as my own little box. So then we take this 2 and we send it in through that. So I get 3 pi divided by 4 plus 2 pi k plus pi L. That's my x coordinates. So now I just took him plus him and divided everything by 2, which I haven't done yet. So divided by 2. And now I do him minus him. This gives me 5 pi divided by 4 plus 2 pi k minus pi L, again divided by 2. So that's how we find the max points, and then similarly you can write up what are the min points and so on. A bit of an odd exercise, I would say, but very useful still as an exercise, I think so. Any questions? So if we go back to the XY plane, we see that actually these yellow points, they align something like this, right? We get some twisted grid, which is more squeezed in one direction than the other direction. Yeah, that's it. Okay, we made it halfway. And to compensate for the other half and the fact that I was absent half an hour, I will do the remaining 3 during lunch hour today, all right? So feel free to come back then and see how to solve the other ones. Thank you for today. And tomorrow, okay, so I will update the schedule, and tomorrow we will have a course revision. So I will just go through the whole course from beginning to end and talk about what's important. All right? Over and out.